last week between when I write and when it shows up on the screen. It's not terrible, but it's a little weird. Okay, so let's look at a couple more examples. So right where we left off yesterday, let's look at the definite integral -1 to 2, let's say negative x cubed plus x squared plus 2x. And we know by definition this definite integral of this function is the limit as n goes to infinity of the Riemann sum, k equals 1 to n, where inside the Riemann sum it's this function, of course f is this guy right here, at some set of selected points times delta x. And the first question I would ask is, what is delta x? Just remember your overall interval is -1 to 2. Yep, Ethan says 3 over n. Remember, that's your formula for delta x. So in this case, it's the overall width of the interval, which is 3, divided by the number of subintervals. So that's your delta x. So in this case, it's limit n goes to infinity. Now, before I fill in that delta x part, let's figure out what we want to put for the ck part. Okay, now, what can I pick for the ck's? Anything I want. We settled yesterday on picking left or right endpoints, and actually we said right endpoints were the easiest. Do you remember the formula that we came up with for right endpoints? That is, if C1 was going to be the right endpoint of the first subinterval, C2 the right endpoint of the second interval, and so on, we actually came up with a little formula for what each one of those CKs would look like. Is that n greater than a under limits n approaches infinity? Anybody have this? Quite. Okay, Ethan says a plus k delta x. Everybody remember that? A is the absolute left endpoint of the entire interval, which in this case is the -1. So I'm going to say each one of those ck's is -1 plus some multiple of delta x. So when I take -1 times 1 times delta, or plus 1 times delta x, it's going to put me here. When I take -1 plus 2 of those, it's going to put me there. And so the point I'm selecting from the first subinterval is -1 plus 1 times delta x. The number I'm picking from the second subinterval is -1 plus 2 times delta x, which would put me here. Same thing for 3. I would add 3 of those. Well, if I add that 3 times starting at -1, it's going to put me 1, 2, 3 right there at the right endpoint of the third subinterval. So generally, what's our ck going to be? -1 plus k times delta x, and we said delta x was 3 over n. So the number I'm going to plug into my function is -1 plus 3k over n. Let's make sure we know how to get that before we go any further. When I multiply this k times this 3 over n, that's where I'm getting the 3k over n. And the 3 over n came from this up here. And then the k is just increasing from 1 to 2 to 3 to 4 and so on. Now we find f of ck. So now it's just writing this out. So let's write that line above. It'd be limit n goes to infinity, summation k equals 1 to n. F of ck means what? It means taking this function, which is f, and plugging this value in for x. So you're saying what? Negative 1 plus 3k over n cubed plus negative 1 plus 3k over n squared plus 2 times negative 1 plus 3k over n. Don't forget the delta x out at the very end, so all of this should be multiplied times 3 over n. Hold on, what did Rebecca say here? So there is a value for k that we could find. Well, no, the k is that index of summation, so the k in this sum is ranging from 1 to n. What we're doing is writing down a formula for each of these points that we're selecting from each subinterval. So that's what this ck formula is. So here's what c1 looks like, c2, c3. When I run through this sum, k is going from 1 to n, which means I'm adding up f of c1 plus f of c2 plus f of c3 all the way up through f of cn. All of those are multiplied by 3 over n, and that's adding up the areas of those rectangles, which is what this guy is. It's an area under a curve. Now, by the way, since I mentioned that, do we know what the graph of this thing looks like? If I took out a negative x, that would leave what? An x squared minus an x minus a 2. Which means this function I've picked factors this way. That means there are zeros at 0 and at 2 and at negative 1. And since this is a cubic with a negative coefficient, that means the tails should go like this. So if I were to graph this, I would see something like this. I'm not saying those proportions are necessarily correct. Now, this brings up a question. So let's talk about this for a minute before we do all the work. If I integrate from negative 1 to 2, this function that you see in this picture, in this example, should I interpret this as area under this curve? And when I say under, I would mean this area and this area. Is that what this integral tells me? Okay, Ethan says the difference, and that's correct. Does everybody see that if I were to integrate from 0 to 2 this function, that would give me this area? Is everybody okay with that? That would be the area in blue. Everybody agree? Okay, why do I know that? Because I know the function is positive everywhere from 0 to 2. So when I construct any Riemann sum on any partition of the interval 0 to 2, all the function values are positive, which means when I generate those rectangles, they all lie above the x-axis. When I add them up, I would be approximating the area under that curve. Okay, now, what happens if I evaluate the integral from negative 1 to 0 of this function? Well, the important part is what? On that interval, all of your function values are negative. Everybody agree with that? I'm just looking at the picture. So here's the thing, what is the definite integral? By definition, it's the limit as n goes to infinity of a Riemann sum, where each term in that Riemann sum is a function value times a width of the subinterval. Well, these are always positive, but on the interval -1 to 0 in this picture, these are all negative. Okay, so question for everybody. When I evaluate this integral, am I going to get a negative number or a positive number for an answer? Okay, what are all of your function values on this interval -1 to 0?
Alright, those are negative. Did you ask, like, from -1 to 0, what it would be?
Yeah, now I think what David and Rebecca may be thinking is that if my picture is correct, if the proportions are correct, I think what David might be thinking is this area over here is bigger than this area, right? And so if you
Yeah, and like the total answer would be positive.
the total answer would definitely be positive. And that's why before Ethan said it would be the difference of the two. And that's what I'm driving at here. Does everybody see that because all of the function values from -1 to 0 are negative, that the value of this integral right here, the one that goes from -1 to 0, that overall integral will be negative. Meaning, what we've been saying all along about integrals being areas under curves, that's really only true if the function is positive, right? Let's just make a note of that. We're saying the definite integral of a function is area, let's say, under a curve if f is positive or non-negative, let's say, on that interval. Okay, what's going to happen if f is negative on that interval? Then you're going to get a negative value, right? And actually, wouldn't it be the negative of the area above the curve and below the x-axis? Meaning, if I calculate the integral from 0 to 2, I'm going to get a positive answer. If I calculate the integral from -1 to 0, I would get a negative answer. And if the proportions in my picture are correct, then when I integrate the whole thing from -1 to 2, it is going to be the difference of those two. I'm going to sum up all the positive area in this piece on the right. I'm going to sum up all of this, if you want to call it negative area, in that little bit on the left. And if the total area of that little piece on the left is smaller than the big area on the right, the difference would be positive. Point being, this integral right here, the original one that we're working on, -1 to 2, should not be interpreted strictly as area under curve. As Ethan said, it's the difference of two areas. Everybody with me on that? Meaning, for me to be able to interpret what this integral is in terms of area, I'm going to have to know what the picture looks like. I'm going to have to know if it's all positive or if some of it's negative. Now, in this problem, notice when I wrote it up, I wasn't asking you to tell me what the area under that curve was. I was just asking you to calculate this definite integral. So there's, two levels here. I can just ask you to calculate an integral. Then we can always ask later on, what does it mean? What does it mean in terms of area? So we've just gone over for this particular picture what we think the answer should mean. And this does all assume that this piece on the right is a bigger area than the one on the left. So let's go ahead and do it and see what we get. Now, is everybody okay with that last line at the top here? This one here. Any questions there before we keep going? I guess the biggest thing is everybody okay with how we're getting that -1 plus 3k over n part. That's the thing we came up with at the very end yesterday. Remember, you could also use left endpoints, and I'll just remind you that the left endpoints would be the a value plus k minus 1 times delta x. Okay, I'm sure you can see that if I start plugging that into the x in negative x cubed plus x squared plus 2x, this one's going to be a little more trouble. Rebecca says, is the reason we have 3 sets of negative 1 plus 3k over n because our original is cubed? Yes. Yep. Oh, I see what you're saying. You mean that, are you talking about the 3 in the actual expression right here?
I think she's asking, like, why we have 3 different, like, pieces, maybe?
I thought she was just looking at the 3 here. I mean, the reason I have the 3 there is just because I have a 3 in the function up here. Now, the 3 here came from this part, that the overall width of the interval was 2 minus minus 1, which was 3, and we're dividing this into n pieces. So that's where that part came from. Gotcha. Okay, now let's work it out. And this is just a lot of picky algebra, so on the other end there, you guys take your time. And expand out everything here. And it will start with a 1. Does it look right? So far, so good.
Hold on, I'm working on the second part.
Okay. Oops, that's not what I meant to shade.
When do we multiply by delta x?
Well, you can do it right now if you want. The only reason I don't do it up front is because once I expand all this stuff in the big set of brackets, there's going to be like terms. And I'm thinking maybe I could combine those first before I absorb that 3 over n in. Or for that matter, you could pull the 3 over n outside the entire summation right now, because it doesn't have anything to do with k. So there's really no set rules on how you need to absorb that 3 over n in. You know, it's just going to get absorbed in eventually one way or the other. I would wait to distribute it though.
Gotcha.
Yep, that's right, Rebecca. Just multiplying out. And then of course if there's anything that I could combine, now would be the time to do that. So for
And go
example,
completely away.
yeah, go ahead.
The ones and like, well, the constants, I guess, the one without any variables, they go completely away.
They do.
I'm for sure, right?
Yeah, does everybody see that? So Ruben's talking about the 1 and the 1 and the minus 2. Looks like they're gone entirely. And then I guess we could go for those k over n terms. So there's, let's see, so there's 1 there, 1 there, 1 there. And that looks like -9, -6, -15, -15 plus 6, we're back to -9. And then we could go for the squares. K squared over n squared, looks like there's 2 of those. Looks like that would be 36. And then I guess we've got those k cubes, but I think that's the only one. So far, so good.
This is around here where we like take the K and leave it by itself, right?
Yeah, so this goes to Ethan's question about what do I want to pull out. Yeah, James is saying, would you reduce that now or later? This is up to you, but here, if you want my suggestions, this is what I would do. I would take all of the n stuff out and split this up into 3 terms right now. So what I mean is, when you look at what's going to happen when you take this times this when you distribute, you can see that there's going to be a minus 27 over n squared times a k. I would just take that negative 27 over n squared right out, times limit, actually, let me back up here. Let's put a big limit outside of everything, because we're still doing the limit on the outside. And so I'm saying when you distribute those 2 green ones, I could take that negative 27 over n squared and pull it outside that summation, and what would be left in the summation would just be a k. And then if I did the same thing with the next 2, there'd be, what, a 108 over n cubed that I could pull outside the sum, and what would be left inside would be a k squared. And then if I do the same thing on the last one, so this one times the guy outside, looks like again I would have a 108. This time it would be an n to the fourth in the bottom, times summation k equals 1 to n k cubed. So I guess the answer to James' question and Ethan's question, when and where, how you pull those things out doesn't matter, but I think this would be the most direct at this step right here. Just simply put all that constant and n stuff together, pull it outside each sum, and now I can do what in the next line? One more thing before I take the limit. I'll say this one's negative 27 over n squared times this guy.
Didn't you say K is like a specific thing? I
Okay.
remember.
Yeah, hold on one second. I did make a mistake here. 3 times 27 isn't 108. Let's try 81. James says that, and that's correct. I think I was still looking at the 3 times 36, I guess. Okay, go ahead, Reuben. Sorry.
I was just saying, like, don't we have to replace the summation K with,
Yep.
I can't remember what it is, dang it.
Anybody got that one? The one I have in yellow there, the summations of the k's.
N times n plus 1 over 2.
Yep. That's the one you're thinking about, Reuben.
Yeah, I remember you made us memorize it, I think.
I suggested you did, but when we did this normal last semester, I put those on the board for you during the test. Of course, when you do them this time.
K squared.
Yeah, so what's that one come out to? That's the one that's got the 6 in the bottom.
N times n plus 1 times 2n plus 1 over 6.
And then this one we didn't use yesterday, but we talked about that one last week too. And that was n squared times n plus 1 squared over 4. Oops.
What is the second part for the K squared? I see the n plus 1. Is that 2 something?
It's 2n plus 1, yeah.
Okay.
Okay, now this next part, I don't mind if you do a little bit of this in your head. You certainly can write out every detail if you want. But when I take the limit of this next part, this part right here, does everybody see the overall degree of the top will be n squared, and the overall degree of the bottom is definitely n squared? And you know that if those degrees are the same, the limit of a rational function where the degree of the top and the degree of the bottom is the same is just the ratio of the leading coefficients. And so again, you don't need to write all this out, but if I wrote out what that was, it would be negative 27n squared minus 27n over 2n squared. And I'm looking at the degrees both being 2, which means the limit as n goes to infinity is the ratio of the leading coefficients. So for the one in green, it should be negative 27 over 2. Okay, what's that next one? Well, let's see. Let me just do a little scratch work. The bottom is 6n cubed. Now, you don't need to tell me what the whole thing is, but if you multiplied out these two, what would the leading term be? Yeah, do 216 with an n cubed in front of it, right? So again, since the degrees are the same, we're back to the limit is the ratio of the leading coefficients, which would be 108 over 3. Same thing on this last one. Yeah, 108 over 3 does come out to 36. So that one's nice. Yeah, definitely n to the fourth in this last one. It's going to be negative 181 n to the fourth for the leading term at the top, and looks like 4 n to the fourth in the bottom. So it looks like negative 81 over 4. Look good? So what does that come out to? That's 135. I think it all comes out to 9/4, doesn't it? If you check that. Check my arithmetic there just to make sure.
It's good.
Yeah. Now, of course, when I drew this, I had no idea what the proportions of those two little loops were. The only reason I made the one over here bigger is simply because the x-intercept was 2 here and it was negative 1 here. So I was assuming that the loop on the right is bigger than the loop on the left. And what this result says is, well, the difference between the loops is not as big as it would necessarily appear in my picture. Basically, what does our result say? That the area of this piece is 9/4 bigger than the area of this piece, because it's counting this part as positive area, it's counting this part as negative area. This integral is the sum of those two, which means it's the difference of those two areas.
Rebecca, on that last part, we were just taking the leading coefficients and adding up the numbers that we got from that. Does that make sense? I don't know.
I think she was okay with what we were doing here, because she's the one that said we had the end of the fourth.
Yeah, she just said her dog was distracting her.
I see that now, yeah. Mine's been forced outside for the time being, so that doesn't happen again, at least not for now.
Is the 144 over 4 the area of just the right piece?
No, it's not, because where's that 144 over coming from? It's coming from this, and that 36 is baked into your Riemann sum here, so you can't really interpret any of these three pieces as a distinct area of one of these loops that we're talking about in the picture.
Okay.
What I can say is, what if I took away, like you said before, if I took away this area, over here, we're saying the remaining part is 9/4, and obviously my proportions are not correct there. Now, one thing is for sure, if I just did the integral from 0 to 2 of this function, I would just get a positive answer, and I could definitely interpret that as this area. So by the way, do you all see that if the question here was, here's this function, here's what the graph looks like, tell me what the area of each of those two pieces is, you would have to integrate this one to find the big area on the right, and you would have to integrate this one, and then do what with that negative answer? Just negate it to turn it into a positive? In other words, the absolute value of this negative answer would give you this area. So let's put it this way. Integral 0 to 2 of f is the area in orange, and the absolute value of the integral negative 1 to 0 f of x dx, that's the area, let's say in green, which is this part. Make sense?
Yeah.
Okay, let's do another one. So nothing different here, just another one for practice. We'll not do a cube this time. We'll step back to just a square. So let's say 0 to 2 negative x squared plus x. So this would just be good practice for you for setting up all the little things you need. So, you know, figuring out delta x, figuring out what your CK looks like, and then finally setting up the Riemann sum itself, simplifying it and then taking the limit. So I guess first of all we figure out the delta x. Which would be
Would it be 2 over n?
Yep. Everybody okay with that part? It's simply
So
the
negative 1 plus 2k over n.
Almost. Okay, you're right. Except where's your starting point this time? What interval are you on?
Oh, 0 to 2. Okay.
Yeah, so instead of negative 1 plus k delta x like it was in the last problem, now it's actually 0 plus k delta x, which is a lot nicer because that means your ck is just going to be k times 2 over n. You see how having the starting point of the interval be 0 means your algebra is going to be much simpler. What made that last one difficult is when you had your cubes and your squares, you were plugging in negative 1 plus 3k over n. The fact that this ck had 2 terms to it is what led to all that foiling and distribution that you had to do. If that negative 1 had just been a 0 instead, this would have just been 3k over n cubed, and you would have been 27k cubed over n cubed, done. Alright, so because this one starts at 0, you already know all the algebra is going to be much simpler. Okay, so put that all together. We know that, just to remind me here, that this is 2 over n. And then for the ck, which is going to be our right endpoints, it's going to be 0 plus 2 over n. 2k over n, which is 2k over n. So now take your limit, form your Riemann sum, plug these ck's into your function. So I guess negative 2k over n squared plus x, which would just be 2k over n. Don't forget the delta x, which is the 2 over n. In fact, this one's easy enough that we could probably do it in our head. I know this part's going to be negative 4k squared over n squared. And again, since the numbers are so easy here, I think I'm just going to combine those two and say that that's negative 8k squared over n cubed. And when I do these two, it's going to be 4k over n squared. So, you know, back to what James and Ethan were saying, do you want to absorb the 2 over n first or last, or pull it outside the sum? Well, in the last one, I deferred it till later because things were more complicated. This one's so simple that I don't think it's that hard to just pull that 2 over n in right now. But the one thing I would retain from the last example is I would split this into 2 sums. And for each sum, I would pull out everything that doesn't involve k. So what would you pull out in the first sum?
But negative 8 over n cubed.
Yep. And that'll just leave that k equals 1 to n k squared. And then what can I pull out in the next one, the last one? Yep.
4 over n squared.
Looks good. Now you know the next thing. You've got compact formulas for each of those. So now you just write down what those are. So this first one would be negative 8 over n cubed times sum of the k squareds, which was that one that had the 6 in the bottom. And then the k's is just our n times n plus 1 over 2. And now at this point is where I don't mind you, like I said, being a little lazy, and not really lazy, but doing some of this in your head. So if I recognize that the degree of the top and the degree of the bottom is both 3 for this first term, then I just have to figure out what the leading coefficients are. And what I see is that for the first one. What do you see for the second one?
2.
Yep. Again, sloppy graph and not proportionally correct. In fact, it's really bad. It's so bad that I don't mind rough graph, but that's a little too rough. So let's see, 0, 0. If you plug in 1/2, it's going to be negative 1/2 times negative 1/2, so it's going to be 1/4. So it's actually way down here somewhere. So the graph of this will look something like this, roughly. Everybody agree? If that's 0, and that's 1, this is 1/4. That's where the vertex is, 1/2, 1/4. Don't really need to know any of that to do this, but the one thing I do see is that if I integrate from 0 to 2, which is what we were doing here, then I'm integrating from here to here. And the whole point is what? When I integrate from 0 to 1, that part of the integral is going to be positive. But when I integrate from 1 to 2, which is the second part of the interval, all of that stuff is all negative, and even with my terrible picture, it does look like that area is larger. I know it is because I know that parabola starts decreasing more sharply once it passes 1. Okay, and that accounts for why I'm getting a negative answer. That negative area between 1 and 2 is outweighing that positive area between 0 and 1. But again, I mean, this is good to look at so we get an idea of what these integrals measure. But when you're doing these problems, like say if I give you this one on a test, the basic Riemann sum limit calculation like I'm doing here, I'm not going to really be asking you to interpret what it means at that point on the test. It's just going to be, can you get through this process and show me the detail and get the value for the integral? But I guess the other thing I'm saying here is don't get thrown when you see a negative answer. Obviously, integrals can yield negative answers. So far, so good? I mean, I'll agree with everything that was said yesterday, like when Brittany and Ruben were saying, looks like a lot of icky algebra detail. True, but once you do a few, it does get to be the same algebra, and once you get used to it, it's not so bad. What do you think?
I have a few
Those are actually really fun.
What was that, Ruben?
They're really fun.
I think so. What were you
I
saying?
pretty enjoy Riemann sums.
What were you saying, Rebecca?
I just have a few questions just to make sure I'm understanding what's going on.
Okay.
So our n value, is that just the end of our domain? So like this one that we just did, our n is 2, correct?
Now, when you say n, you mean, are you talking about the letter n, as in this guy right here?
Where are you? Hold on.
Yeah, sorry, it takes a second for it to, there's a little delay now. I don't know what that's about.
For when we're finding delta x.
Okay, yes, for the delta x, if the integral is from a to b of the function, then we're saying delta x is b minus a over n. So in our example here, we said it was 2 minus 0 over n.
Okay. That makes sense. All right. The second question is: are we going to need to graph in this chapter in 4.5?
Yes, you will need to do a little graphing. Now, for the stuff in 4.5, no. So that's what I was just saying. I just want you to be able to calculate definite integrals by taking these limits. The interpretation that I'm talking about down here, you'll need to do that eventually, not for this kind of problem that we're doing here in 4.5 though. But it's a good time to start looking at it.
All right. I just wanted to make sure. Thank you.
Yep. Okay, let's look at some properties of the definite integral, which are pretty easy things, all pretty intuitive. So number one, if I take a definite integral of a function and my upper and lower limits are the same number. So for example, if I took the integral from 5 to 5 of x squared dx, what should I get? I wish I had a cute emoji to send back to you. I don't know how to beat that though. Egg, chick. There you go. That's pretty good.
Oh, dang.
Yeah, that is
That's
good.
brutal. What the heck? Alright, what was the question?
I forgot. If your upper and lower limits in the integral are the same number, what should that equal?
For 1?
Yeah, Ethan says 0.
0.
Okay,
Yeah,
does
I
that
think
make
it's
sense?
0 since, it's a line.
Yeah, you know that these form your delta x, right? And so what you're saying is your delta x is 0 because your interval has no width. If I am going to interpret this in terms of area, you don't have a two-dimensional area. There is no area because your interval has no width to it. So it would make sense that if I tried to integrate some function from a lower limit to an upper limit using the same number, I should get 0. So most of these properties are going to be like this. They're going to be common sense things. Second one, this one's not so much common sense as a definition, although if you think about what it's saying, it does make sense. If I integrate from b to a of a function, how is that going to relate to the integral from a to b? That is the one where I switch the two limits. Yeah, Reuben says a negative, right? So if it was going from a to b, if that's where the numbers were, then I know this integral on, this integral on the right would be interpreted as the area under the curve, and I know how we build that. We break it up into subintervals. On each subinterval, I take the right endpoint minus the left endpoint to get the delta x for that subinterval. Okay, what would it mean if you tried to construct the Riemann sum for this one on the left? Well, every time you formed a delta x, you would be taking a smaller x value minus a bigger x value, which means your delta x would be negative for every subinterval. Meaning, if you construct this integral on the left, where your lower limit is the bigger number and your upper limit's the smaller number, that's going to be the same as the negative of the integral that goes from the smaller lower limit to the upper bigger limit. In other words, if you switch or interchange those limits of integration, you're going to get the opposite sign on your integral. This is an important one. We're going to use this a few times. Property number 3, okay, nothing fancy here. You guys know this one already. Since the definite integral is a limit, and we know that when you take limits you can move constant multiples in and out of the limit, that means when I take the definite integral of a constant times a function, I should be able to pull that constant outside of the integral. So it's that same old property we've seen many, many times. Here's another one that's fairly obvious. If I take the definite integral of plus f plus or minus g, Rebecca says, would that be affected by the limit? You mean the constant? The c? Yeah, it won't be. It's like when I take the limit, let's say, of 5 times a function. We proved a long time ago that constant 5, it does, well, let's put it this way, it does affect the value of the limit, but it doesn't affect the limit of the function part that has the x in it. Right, so that limit property always said we could pull multiplicative constants outside the limit. Okay, so haven't we seen this rule over and over again? We can pull constants outside of derivatives. We can pull constants outside of integrals now, because what are integrals and derivatives? They are both limits. That's really the big thing here. Now actually number 4 is kind of in the same vein. What have we said way back at the beginning of this class? Limits of sums or sums of limits. Derivatives of sums or sums of derivatives. Now we're just saying the integral of a sum is the sum of the integrals over that same interval. That one shouldn't be too surprising either. The next one, though, let's say we had a function, let's say this is a, let's say this is b. Let's just say for convenience in our picture that everything's positive there. Let's say I pick some number in between a and b, like c. Okay, what can I say about the integral from a to b, which is...
The integral from a to b is equal to the summation of the integral a to c and c to b.
Good. Does that make sense? We're just saying that, at least for this picture, we'll split this overall area into 2 little sub-areas. And the overall area should just be the sum of those 2. Would that still be true if let's say our function was sometimes negative and sometimes positive. If this was A and this was B, would it be true if I split the two right there? Would the overall integral from A to B, which is obviously going to be some positive stuff and some negative stuff, would that be the same as just taking the integral from A to C, which would be the positive stuff, plus the integral from C to B? Yeah, just watch the signs is correct. Okay, now also I could split it somewhere else. It wouldn't have to be right there. It could be here. Well, if I integrate from A to C, some of that's positive, right? And some of it's negative. And I know when I integrate from A to C, it's going to be the difference of the positive area and the negative area, plus the integral from C to B, which would be the rest of the area, which would be negative again. So it looks like I should be able to split it wherever I want, regardless of whether some of that area is above the x-axis or not. Question. Let's go back to this picture. Let's say A is here. Let's say B is here. Let's say C is here. Which means integral from A to B is this part, right?
You would just subtract it.
Yeah, that's right. Okay, so let's write out what they look like. If this is still correct, the integral from A to B is the one I just shaded in red. What's the integral from A to C? It's the whole thing, isn't it? Correct? And so if I wanted the red part, if I wanted this part, wouldn't I have to take the green part, which is the integral from A to C, and subtract the area that's between B and C? Which is, let's say, this part. Does everybody see that? If I want the green, which is the integral from, I'm sorry, I'm saying this wrong. If I want the integral from A to B, which is the red, then I want to take the green, which is the integral from A to C, and subtract out the purple, which is the integral from B to C. Does that look right so far? So in the picture I'm saying this is the red, I'm saying this is the green, I'm saying this is the purple. Does that look right? But what is this guy right here? If I think about this and these guys, because right now what's the problem here? I'm trying to show that this is true, and it looks like I almost have it, except these are in the wrong places. Yeah, that's the one we just did a minute ago that said if we switch this sign, we can just interchange these two limits. And so if we do change this to a positive, that's going to interchange these two limits and make this a C and make this a B. And then notice when you put these two integrals together, this first one starts at A, this one ends at B. I'm sorry, it ends at, ends at B. And notice the first one stops where the second one starts, which is how this theorem works up here. It says that I go from A to C plus the second integral starts at C where the first one stopped and then goes to B. Okay, the point here is what? And let me just write it here just so we're clear on this. In this property, A, B, and C are any numbers. Okay, meaning it doesn't have to be A and then B and then C is in the middle. These little pictures I'm drawing here are just meant to justify or convince you that this theorem, or this property number 5, applies regardless of the relationship between those numbers. So that B can be in between A and C, or it can be outside the interval A to C. It doesn't matter, no matter how you configure the three numbers. If you draw these pictures, it'll make sense that this property is always true. This one's also important. We'll use this here a bit in this chapter some more. Okay, let's get through the last couple, which are pretty simple. Number 6, also an important one. So let's say I've got a function. Let's say that's A, let's say that's B. And so of course the integral from A to B, I would visualize that as the area. Okay, by the way, what's our big theorem? It says we know a function is integrable if it's continuous. Continuity of the function is the thing that guarantees me this definite integral exists. So let's say this is a continuous function. Is it clear that a continuous function is always going to have a max and a min on a closed interval? There's always going to be an absolute min, absolute max. It does look like in this picture I've created the max to be maybe right there. Does that look right? If I created a rectangle that basically looked like this, what's the area of that rectangle? Here, let me give you a number to work with. Let's say big M is the place where that absolute maximum happens on A to B. Then what's the area of that red rectangle?
Would you do like F of A times F of M?
Not quite.
I think, well, no.
What's the width of the rectangle?
The distance between A to B, or B minus A, I guess.
Yep, good. What's the height?
F of A.
Not F of A. Not necessarily. It's whatever this maximum is, right?
Oh, F of M.
F of M. And I don't know where that is. I just know it's going to happen somewhere because this is a continuous function on a closed interval. So if you wanted to, let's just call this B minus A times the maximum of F on the interval A to B. Let's just say that. Am I also guaranteed that there'll be a minimum somewhere on that interval?
Yeah.
Yeah, and in fact, in this picture, it looks like it does happen at A. What's the area of that rectangle? It would be B minus A times the minimum of the function on that interval. And I know that happens somewhere. Everybody with me so far? What can I say about the value of the definite integral? What's it between? And we've actually used this idea a couple times before. Well, that definite integral is the area under the curve, right? So it's the true area under the curve. And that area is bounded above by the area of the larger rectangle, which we said was...
Were you overshooting the square and then undershooting, I guess?
And now we're just rewriting that down as an inequality. We're saying if we overshoot, the most we could overshoot using function values in this picture would be B minus A times the maximum function value. And I'll just write that like that. That's just shorthand for maximum of the function on that interval. and I could undershoot it by using function values by going all the way down to b minus a times the minimum of the function on that interval. Did you just not hear that last part about, so we're just going to say the area under the curve is less than or equal to this thing on the right, which is just b minus a times the maximum of the function. Oops. Well, I don't know what's happening. Is it cutting out for everybody else too? Anybody else having trouble hearing me? Anybody else?
Okay, there, it's better now.
Yeah, I don't know what happened. I didn't do a thing. Okay, we'll go.
Yeah, like I could not hear anything.
Weird. Yeah, I didn't change anything. Okay, so this theorem just says what? That I have a natural upper bound and lower bound for the integral, just in terms of b minus a times a maximum function value. And the picture is our justification for that. Okay, I think there's just one last one. It actually is two parts, but yeah, this one's real easy. Okay, if no sound at all for Andrew. Yeah, I'm not sure what would be going on there, because you've heard me other days. Well, Andrew, just, well, of course he can't hear me. Andrew, you can always look at the video when I post it. Better audio quality, David says. Yeah, that's right, if I get around to posting it, which I will. Okay, so last one, if f of x is greater than or equal to 0, what can you say about the integral of such a function? Yeah. Does that one make sense to everybody? Yeah, if the function's never negative, that means when you're forming the Riemann sum, none of the function
He's
values...
already put an angry face.
What was that?
Ethan put an angry face.
He does look rather angry.
Hold on, I'm looking. Who looks angry? Oh, I see.
He thinks my greater than or equal to looks angry.
I see.
Yeah, sorry, it just reminded me of that. I'm sorry.
You gotta go with gotta go with what you see. Okay, what can I say about these two? If f is greater than or equal to g, would the integrals be the same way?
Yes.
Because if that's true, I know this is true, right? And if we believe this one, which by the way, there is a formal proof you can do for that, but if we knew that, then if f was bigger than g, f minus g would be bigger than 0, and then if I applied this one, that would say that the integral of f minus g is greater than 0. But what's the integral of f minus g? It's the integral of f minus the integral of g. But if I add the integral of g to both sides, that just says the integral of f is greater than or equal to the integral of g. So let's just say if I know this one, if I know this one follows. Or if I knew this one follows. Those two imply each other. So, if I know a function's positive, the integral will be positive. If I know one function's bigger than another, the integral of the bigger function will get me a bigger value than the integral of the smaller function. So nothing really crazy with these properties. Half of them are limit properties you already knew. Two of them are sort of definitions. I'd be thinking about this one and this one, although they're easy to justify when you draw some pictures. The rest of these involve estimates. Number 6 is using the upper and lower estimates, which is basically our circumscribed and inscribed rectangles. And then number 7 is just talking about bounding integrals by looking at which function is bigger. So if those all make sense, your homework will ask you a few little questions about these, which are pretty easy questions. But then we'll need some of these with what we're going to start doing tomorrow. So you've got your homework for 4 or 5. I'm also going to put up some Blackboard problems. I'll put those up here this afternoon. There'll be 5 to 6 of those. Those are limit of Riemann sum problems, like the ones we've been doing here. Those will be for turning in. Let's see, it's Tuesday, so turn them in just like you did your take-home tests. Write them up on paper. You guys can just send it to me like you did before. This time I'm going to ask you all to try and turn them in the same way. I got different formats and had some trouble with some of them. So we'll go over that later, but for right now, just work your problems on paper. Are we going to have any mom homework? Yes. You'll get that pretty soon. So one thing at a time. You've got your homework for 4 or 5. I'll put the Blackboard stuff up today. Your mom homework, if it's Tuesday, probably Thursday, I'll put that up. Sound good? Are we going to have... Sounds good. I think Ruben's ready to go. Have a nice day.
I'm actually just hungry.
Ruben is looking, yes, isn't he? The combination of Pablo and the... overwhelming almost.
Yeah, this quarantine has made my hair exactly like his. Super long.
I'm having a hard time seeing that.
Everyone have a good day.
Bye all. See you in the morning.